In section 2.6, we are going to analyze graphs of functions and also talk about a concept known as rate of change. First, let's discuss even and odd functions. So in the graphs here, we have the function f of x is equal to x squared, which has this shape. And on the right, we have f of x equals x cubed, which has this shape. Now, what I want you to notice is that for the graph f of x is equal to x squared, when you plug in a positive value of x, you get a particular y value. And when you plug in the opposite of that number, you get the same y value. And this happens for any two values of x that are opposites. So as an example, we can see that f of 2 is equal to 2 squared, which is 4, and f of negative 2 is negative 2 squared, which is also 4. Since this happens for all values of x, you can see that we have symmetry across the y-axis. When you have symmetry with respect to the y-axis, we call this an even function. For the other function, f of x is equal to x cubed, you have a different kind of symmetry. When you plug in a positive value of x, such as this value here, you will get a particular y value. And when you plug in the opposite of that value of x, you will get the opposite of that y value. So the symmetry here is that if you draw a line directly from one point to the other, you'll notice that it will always go through the origin. So in this graph, we say that it has symmetry with respect to the origin. And to see an example of that, we could plug in the value of 2. So f of 2 for this function is 2 cubed, which is 8. And if you plug in negative 2, you get negative 2 cubed, and negative 2 to the third power is negative 8. So what you should see is that these values are opposites of each other, and that is why you have this symmetry through the origin. When this happens for all values of x, we say the function is odd. All right, so now we will go to an official definition. So the official definition for an even function is that a function is symmetric with respect to the y-axis if f of x is equal to f of negative x for each x in the domain. Functions with this property are called even functions. And the definition of an odd function is a function is symmetric with respect to the origin if f of negative x is equal to negative, this should be f of x there, for each x in the domain. And functions with this property are called odd functions. So let me just go back to the previous examples and let's talk about why they are even and odd for those particular functions. So one of the functions that we had was f of x is equal to x squared. If you plug negative x into this function, you will get negative x to the second power, which means negative x times negative x, which is basically positive x squared. But notice that positive x squared is f of x. So we can say that this is equal to f of x. So in the end, you can see that f of negative x is equal to f of x. And when this happens, we say the function is even. For the other function, f of x equals x cubed, f of negative x is negative x to the third power, which means negative x times negative x times negative x. When you multiply three negatives, you get a negative, and x times x times x is x cubed. This is not the same as the original function. The original function was x cubed, so what we have here is negative x cubed. So that is the opposite of the original function. So in this case, f of negative x is equal to negative f of x. And that's what it means for a function to be odd. So we can algebraically test to see if a function is even or odd by simply plugging in negative x and seeing what happens. So now let's go ahead and look at our first official example here. Using the definitions of even and odd functions, classify the following functions as either odd or even or neither. So in our first example here, we have f of x is equal to the absolute value of x plus 2. So what we need to do is plug negative x into this function and observe what happens. Well, when you plug negative x into here, you get the absolute value of negative x plus 2. Well, the absolute value of negative x is the same as the absolute value of x. That's a property of absolute values. So f of negative x ends up being the absolute value of x plus 2, and that is our original function. So that is f of x. So in the end, you see here what we have is f of negative x is equal to f of x, which means our first example here is an even function. In the next example, we have g of x is equal to x minus 4 to the second power. So we need to see what happens when we plug in g of negative x. Well, g of negative x is negative x minus 4 to the second power. What can we do with this? Well, you can actually factor a negative out of that, which will give us negative quantity x plus 4, and then that whole thing squared. Remember, a negative is like negative 1. So what I have here is negative 1 to the second power times x plus 4 to the second power. But negative 1 to the second power is positive 1. And so what I end up with here is x plus 4 to the second power. Notice that this is not equal to g of x, right? Is not the same. This is not the same as the function we started with. It's also not equal to the opposite of g of x. So this is an example of a function that is neither even nor odd. And in our third example, we have the function h of x is equal to negative x cubed plus 3x. To test to see if this is an even or an odd function, we are going to plug in negative x. You have to be careful when you do this. We have negative, and then x cubed becomes negative x cubed plus 3 times negative x. So what we're doing here is we're replacing both of these x's with negative x. So what we end up with here is negative, and I'm going to show my work. This would be negative x, negative x, negative x, and then 3 times negative x is negative 3x. If you look at what you have here, you have a negative times a negative is a positive, and a negative times a negative is a positive. So we end up with x cubed minus 3x. Now, is that the same as our original function? Keep in mind, our original function was negative x cubed plus 3x. No, this is not equal to h of x. However, if you factor a negative out of this, you would get negative x cubed plus 3x, right? So when you factor a negative out of these terms, they just become the opposite of what they were. But now notice that this is the same as your original function. So this is equal to negative h of x. So when h of negative x is the same as negative h of x, we say that this function is odd. Now, let me bring in some graphs to show you why these functions are even and odd. So in the first one here, we have the absolute value of x plus 2, which is this graph right here. Keep in mind that this is not that difficult to graph. You would just need to plug in some x values and find some f of x values. But I want you to notice that if you look at the graph, it does have symmetry across the y-axis. And that is what happens when the function is even, which confirms what we got algebraically. Now, if you look at the second graph, that graph is here, And you'll notice that there is no symmetry across the y-axis. There is also no symmetry through the origin. And that's why this function was neither even nor odd. And finally, the last function here, if you sketch a graph of it, it'll have this shape. And I want you to notice that there is symmetry through the origin here. And when a function has symmetry through the origin, we call this an odd function. So I only bring in these graphs to reinforce the idea of what does it mean for a function to be even or odd from a graphing perspective. The next concept I want to discuss is the concept of increasing and decreasing and also constant functions. So we say a function is increasing on an open interval I if for any two numbers in the interval with a less than b, f of a is less than f of b. Okay, we'll talk more about that in a minute. What does it mean for a function to be decreasing? Well, for the same situation there, if a is less than b, f of a is bigger than f of b. And to be constant, f of a would have to be equal to f of b. Now, what it means on a more simple level is that a function is increasing if it is going up. And it is decreasing if it is going down. And it is constant if it is flat. And when I say going up, going down, and flat, I'm talking about reading the graph from left to right. So let's take a look at the example below here. What we want to do here is find the intervals on which the following is true. Where is this function increasing? Where is it decreasing? And where is it constant? So first, let's talk about where it's increasing. Now, if you look at the graph and you read the graph from left to right, we'll just trace it out. The function is doing this, and then it goes here, and then it comes down here, and then across, and then here. When it's increasing, we want to look at when is the graph moving up. So as we move from left to right, here you can see we are going down, so that is not increasing. But from this number up to this number, it's going up. So this piece of the graph is the first part where it is increasing. After that, you can see that it's going down, and then it is flat, and then right here it is going up again. So it is increasing on these two sections of the graph. So now I just need to say, for which interval is that happening? So if you look at the x-axis, you can see that the function is going up from x equals this number, which is -2, up to x equals this number, which is 0. So it is increasing on the interval from -2 up to 0. Union, it is also increasing right here, and that goes from x equals 4 up to x equals 5. Now let's take a look at where is it decreasing. So to be decreasing, we need the function to be moving down. Well, we already kind of talked about it. The function is moving down right here. And the function is also moving down right here. So for which values of x does that occur? Well, it starts moving down from here to here. So on the x-axis, that is from -4 over to -2. So we'll write that here from -4 to -2. Union, it is also moving down from this point to this point. And on the x-axis, that starts at x equals 0 and goes over to x equals 3. And finally, where is it constant? Well, it's constant when the graph is flat. And this little section right here is the only place where the graph is flat. So where does that happen? Well, it happens from here to here, and that is from x equals 3 to x equals 4. So when you're stating where it is increasing or where it is decreasing, you are looking at the x-axis and giving the values of x for which the function is either going up or going down or flat. The next concept is a really important concept, and it's called the average rate of change. So it is important to know when a function is increasing or decreasing. If a function is increasing or decreasing, it is changing. But what is more important to know is how quickly a function changes. How fast does it change? And one measurement for this is the average rate of change. So we have a definition for the average rate of change. If you are on a particular interval from x1 to x2, the average rate of change is computed by f of x2 minus f of x1 divided by x2 minus x1. Now, this should really look familiar to you. If you think of f of x2 as being y2 and f of x1 as being y1, and you make that substitution, this should remind you of the slope of a line. And that is indeed the formula for the slope of a line. However, this average rate of change can be applied to any function, not just lines. So let's go ahead and do an example here. So in our first example, we want to find the average rate of change of the function f of x equals 2x squared plus 1 on the following intervals. We'll take these intervals one at a time. So our first interval is from -3 to -2. So what that means here is when you're looking at this interval, -3 is x1, -2 is x2, and the formula for the average rate of change is f of x2 minus f of x1 divided by x2 minus x1. Now I'm just going to substitute these values in. So x2 is -2, so we're going to have f of -2 here, minus f of x1. x1 is -3, so that's going to be f of -3. And in the bottom, we have x2 minus x1, which is simply -2 minus -3. So now what we need to do is we need to compute the values of f of -2 and f of -3, and we do this by using the function itself. So f of -2 is 2 times -2 squared plus 1. This is 2 times 4 plus 1, and this is equal to 9. And f of -3 is 2 times -3 squared plus 1, which is 2 times 9 plus 1, which is 19. And so when we compute this average rate of change, we're going to have f of -2, which is 9, minus f of -3, which is 19, divided by -2 plus 3. And if we do the math on this, we get -10 divided by 1, which is -10. So the average rate of change on this particular interval is -10 for this function. Now let's do part B. So for part B, we have the interval 0 to 2. So 0 is our x1, 2 is our x2. So our average rate of change is going to be, once again, f of x2 minus f of x1 divided by x2 minus x1. If we plug in the values for x1 and x2, we get f of 2 minus f of 0 divided by 2 minus 0. Now we need to compute what is f of 2 and what is f of 0. And again, we use the function to do this. So f of 2 is 2 times 2 squared plus 1. This is 2 times 4 plus 1, which is 9. And f of 0 is 2 times 0 squared plus 1, which is 2 times 0 plus 1, which is 1. So f of 2 was 9, f of 0 was 1. And if we do the math on that, we get 8 divided by 2, which is 4. So the average rate of change on this particular interval is 4. Now, I would like to take a quick look at the graph to kind of show you what we did geometrically. So here's the graph of the function f of x equals 2x squared plus 1. I want to take a look at what we did graphically. So what we did is we found the average rate of change on the interval from -3 to -2. Here is -3, here is -2. The function value at -3 is 19. The function value at -2 is 9. And remember what we did. We took f of -2 minus f of -3 divided by -2 minus -3. And this was 9 minus 19 divided by -2 plus 3. And that was -10. What we basically did there is we found the slope of the line going through these 2 points. Okay, so notice that that line is what we call a secant line. It is a line that intersects the curve in 2 points. And the slope of that secant line tells you the average rate of change of this function from this number to this number. Then what we did is we did the same thing for the interval from 0 to 2. That was the second part. F of 0 is 1. F of 2 is 9. And what we did was f of 2 minus f of 0 divided by 2 minus 0. And this was 9 minus 1 divided by 2 minus 0, and that is 4. Now, what we did there is if you graph the line through those 2 points, you get another secant line. And the slope of that secant line was positive 4. Okay, and the slope of this secant line over here was -10. So the average rate of change from x equals 0 to x equals 2 is positive 4. Well, that's because the general feature of the graph here is that it's going up. It's increasing, right? So it has this positive average rate of change. Whereas over here, the graph is going down. Right? It's decreasing. So it has an average rate of change that is negative. Okay? So when you're finding the average rate of change, all you need to do is use this formula. But graphically, what you are doing is you are finding the slope of the secant line. That's going to be important later on, especially in calculus. Okay, the next concept we want to discuss is the concept of a difference quotient. The difference quotient is another way of saying the average rate of change. So it is exactly what we just got done discussing in the previous example. Now, the basic concept is that if you start at a value x1 and you call that value a, and your next value is x2 and you call that a plus h, then the average rate of change, which remember is f of x2 minus f of x1 divided by x2 minus x1, well, that's just going to become f of x2, which is f of a plus h, minus f of x1, which is f of a, divided by x2, which is a plus h, minus x1, which is a. And if you simplify this here, these a's cancel out, and you end up getting this expression, f of a plus h minus f of a divided by h. This is an alternative way of describing the average rate of change. So don't be confused by the different symbols, and I know it looks slightly different. It's the same thing. All right, let's go ahead and take a look at this example. So here it says, a ball is dropped from a height of 100 meters. At time t in seconds, the height of the ball from the ground is given by f of t equals negative 4.9 t squared plus 100. Calculate the following. So in part A, we want to find the average rate of change of f on the interval from 1 to 3. Now, just to remind you, the average rate of change is basically this formula right here. We are doing this on the interval from 1 to 3. So 1 is going to be our first time, we'll call that t1, and 3 will be our second time, we'll call that t2. So our average rate of change here was going to be f of t2, which is f of 3, minus f of t1, which is f of 1, divided by 3 minus 1. Now we need to figure out what is f of 3 and what is f of 1. We do this by plugging it into the function. So f of 3 is negative 4.9 times 3 squared plus 100. This is negative 4.9 times 9 plus 100, and you can plug that all into a calculator. And if you do that, you will get 55.9. And f of 1 is negative 4.9 times 1 squared plus 100. And this will be negative 4.9 times 1 plus 100, which is 95.1. So now coming back to the average rate of change, this is going to be f of 3, which is 55.9, minus f of 1, which is 95.1, divided by 3 minus 1 is 2. And if we do the math on that, we get negative 39.2 divided by 2. And when we divide by 2, we get negative 19.6. Now, what is this measuring exactly? Well, it's measuring the average rate of change of the function, and the function measures the height of the ball. So this is measuring the average rate of change of the height of the ball. And, oh, by the way, this should be negative. So this negative 19.6 is basically an average velocity. It's negative 19.6 meters per second. Now for part B, they want us to find the difference quotient. Now the difference quotient is a little bit more abstract because notice when they say to find the difference quotient, they don't give you a particular value for A, which means you're going to leave it in the form A plus H, right? So f of A plus H minus f of A divided by H. So let's go through and calculate the difference quotient for this. So to do this, first of all, we have to compute what is f of A plus H. Well, f of t is this function. So f of A plus H will be negative 4.9 times A plus H squared plus 100. This is negative 4.9 multiplied by A squared plus 2AH plus H squared plus 100. And this is negative 4.9 A squared minus 9.8 AH minus 4.9 H squared plus 100. So that is f of A plus H. Then we have to compute, well, what is f of A? Well, f of A is the same as f of t, but we're going to replace the t with an A. So that will be negative 4.9 A squared plus 100. So now to figure out the difference quotient, I need to take f of A plus H minus f of A and then divide it all by H. So f of A plus H minus f of A divided by H is we're going to take this quantity, we're going to subtract this quantity, and then divide by h. All right, so here is what that looks like. Now, of course, what we need to do here is distribute the negative sign. And when we do that, we get the following. And then notice that we have negative 4.9a squared, positive 4.9a squared cancel out, positive 100 and negative 100 cancel out. And so this expression becomes negative 9.8ah minus 4.9h squared divided by h. And then we can conveniently factor out an h in the numerator. And if we do that, we get h times negative 9.8a minus 4.9h all divided by h. And then what happens is these h's cancel out. And we end up getting negative 9.8a minus 4.9h. So this is the difference quotient for this particular function. Now, I'm going to take that value and save it, and I'm going to show you how what we did in the first part is the same as what we did in the second part. All right, so here's our difference quotient, negative 9.8a minus 4.9h. In the first part of the problem, we found the average rate of change on the interval from 1 to 3. The interval from 1 to 3 means that T1 is 1 and T2 is 3. Well, when you think about this as a and a plus h, the first value here is your a value, and the second value is your a plus h value. So h is equal to the distance from here to here, and that distance is 2. So on this particular interval, a is equal to 1 and h is equal to 2. If you plug in the values of a equals 1 and h equals 2 in here, you get negative 9.8 times 1 minus 4.9 times 2. And this is negative 9.8 minus 9.8, which is negative 19.6. And if you remember, the answer that we got for the first problem was that the average rate of change on the interval from 1 to 3 was negative 19.6. So what we did in the second part is we found a more abstract version of the average rate of change, and it's called the difference quotient. But they're really the same thing. And I know that this won't make sense necessarily the very first time you do a problem, but as you do more and more problems, you will come to realize that these two things are identical. Okay, one last example I want to talk about here is to find the average rate of change for a linear function. So that is the function f of x is equal to mx plus b. And we want to do this on some interval. So we'll call this on the interval from x1 to x2. Let's see what we get. So the average rate of change, remember the definition, it is equal to f of x2 minus f of x1 divided by x2 minus x1. What is f of x2? Well, f of x is mx plus b. So f of x2, we are going to plug x2 in for x. So we get m x2 plus b. F of x1 is very similar. It's going to be m times x1 plus b. So the difference quotient, the average rate of change is f of x2, which is mx2 plus b, minus f of x1, which is mx1 plus b, all divided by x2 minus x1. If we do the math on this, we get mx2 plus b minus mx1 minus b. So what I'm doing here is I'm distributing that negative. And this is divided by x2 minus x1. Notice that the b and the negative b cancel out, and we are left with mx2 minus mx1 divided by x2 minus x1. If you factor out the m on top, look at what happens. We can now cancel these factors out, and you'll notice that you just get m. Yeah, so what is that? Well, the average rate of change for a linear function is m, because what is m? M is the slope of the line, right? So the average rate of change for a line is the slope. All right, that's it for this one.